let's begin our introduction. So today is a very basic intro about what this course is about, the basic ideas of this course, etc., etc. Data is everywhere, right? Data is everywhere. We have a bunch of data, right? So this is some shopping data we can use for economic analysis. We have people's rating of different movies, which is a different kind of data, right? We have documents, which is a different kind of data, right? We have financial markets, which is another different kind of data, and we also have social network, right? This is sentiment analysis. This is about this is the tweet sent by Donald Trump in a single day, from 3 a.m. to 9 p.m. And these are positive tweets, these are negative tweets, and you can see the patterns, right? This is the time where he tweets the most. Here says, why would Kim Jong-un insult me by calling me old? I would never call him short and fat, right? This is his tweet, okay? So anyway, the point is, we live in an age of big data, right? And big data is a concept that has no definition, but basically it means we have lots of data, and not only lots, but all these data have different kind of format, right? So they're organized differently, they are storage differently, there are different kinds of data. And modern data analysis is really about trying to find all different ways to analyze many different kinds of huge quantities of data, right? This is what modern data science is about. Now, what I like to call data science, I really like to encompass everything, right? Not only traditional statistics, but of course machine learning, but also econometrics. Okay? But what's the difference between them? By the way, you have all taken at least one semester of econometrics, right? Have you? Have all of them? I know some of you haven't, but have the majority of you taken one semester of econometrics? Okay, all right. Who taught the course? Michael. Okay, all right. Okay, very nice. And what software do you use? What do you use? R? Do you use? Do you Slate? Oh, okay, very nice. Okay, all right. So what is the you're already familiar with some part of econometrics, but what is the difference between machine learning and statistical econometrics? Right? What are the differences between them? Well, they have, to me at least, they all fall under the umbrella of data science. They all try to do kind of similar things. Okay, so as we will see, they share many similarities, despite the fact that they are developed in different disciplines, right? So machine learning is developed by by CS, okay, computer science department, statistics by statistics, econometrics by economics. They are developed by different disciplines, so they use different language, and they have different terminology. But underlying all of them, there's a lot of similarities. Then there are dissimilarities, as we will see. Okay, so part of the goal of this course is to give you a unified introduction, so that after this course, you basically know what all these disciplines is about. Okay, that's sort of like an ambitious goal of this course, to equip you with an understanding about what all these things is about. Okay, so that give you a foundation for you to pursue future study in whatever direction you want. Okay, but they have difference in their focus and in what they're trying to do. In terms of the focus they have. Machine learning is in particular focused on prediction and pattern discovery. Okay, it's about finding patterns in the data and then trying to use those patterns to make accurate predictions. That's what traditional machine learning is about. Now, what econometrics is about, traditionally, is more about trying to understand or trying to infer causality, causal inference, the cause of X on Y. Okay, what is the causal effect of X on Y? Not only the pattern, but also the causal effect is the traditional focus on econometrics. So understanding causality and the underlying mechanism. Because why? Because economics is not only about making predictions, but economics is a social science, right? As a social science, we try to understand. Okay, we not only try to make prediction, we try to understand what's going on. So we need a lot of estimation of causal effects and the underlying mechanism. So these disciplines have different focus, and they are developed by different disciplines. But as we will see, there are a lot of commonalities, and I hope to bring them together in this course. Right. So talk about commonalities, right? Talk about commonalities. Many things that these disciplines do that seems very different, in fact, are very similar things. Okay, so let's take a look at a typical classification sort of problem in computer science. Okay, so in computer science, a typical problem is called a classification, which is I want you to classify something as, for example, I give you all these pictures. Which one is a chair? Is this a chair? Yes. Is this a chair? No. Is this a chair? No. Right? I give you a picture. Tell me whether this picture is a chair or not. This is called a classification. So basically, classification is about trying to find something which is yes or no. Okay? Yes or no. Or I can say whether it's 0 or 1. Okay, 0 or 1. Right? So if this is a chair, it's 1. If this is it is not a chair, it's 0. That's called classification. Do economics do classification? No, of course. Okay, we do lots of classification in economics as well, right? This is a typical example in business, where I give you a credit card applicants, right, or many credit card holders, and you tell me whether this credit card holder is going to default or not. Okay, whether it's high risk or low risk, is going to default or not. So so these are data. This is how much income these people earn. This is how much balance they currently have. And these are the people who are actually defaulted, and these are people who do not default. So I want you to predict whether a person will default or not based on these two variables, okay, based on this information. And this is essentially a classification problem. Okay? Basically, I give you a person, and tell me whether this person is going to be 1, default, or 0, not default. Okay? So 1 is default, 0 is not default. Just tell me 1 or 0. That's a classification problem. Right? So it looks like these two are very different problems, but they are all classification, and they share very similar algorithms. Okay, when we try to do them, right? Now, in fact, in economics, even more common example is we try to predict people's behavior, right? People's choice. So, is this person going to buy this car or not? Okay? If he's going to buy this car, it's 1. If he's not going to buy this car, it's 0. So just like a chair, is this a chair or not? Chair or not? It's a classification. Is this company going to enter this market? If the company is going to enter this market, it's 1. If the company not enter the market, it's 0. So it's again a classification problem. Okay. So economics, computer science share many similarities in terms of what they try to do. Now, in fact, then we have regression. Okay, then we have regression. So anyone tell me, because I think most of you have studied regression, so anyone tell me what is the definition, what is regression? What is regression? Can you do any definition? Do you know what regression is? Is drawing a line of regression? I think that's what you probably learn in econometrics, right? Now, in a very broad sense, classification. If I give you a y variable, and I want you to predict this y. Okay, I want you to predict this y. Now, if this y variable is discrete, okay, if it's 0, 1, or maybe 2, 3, okay, if this y is discrete, and I want you to predict whether it's 0 or 1 or 2 or 3, then it's called a classification. Okay? Called classification. If y is continuous, not discrete, then it's called a regression. So regression is really, in a broad sense, anytime you have a y variable that is continuous, we call it regression. Now, linear regression is what? Linear regression is regression by drawing a straight line. Right? That's what linear regression is. Okay. All right. So this is in what? This is in agriculture, right? In agriculture, we use regression to study how we can use temperature to predict the yield of corn, right? The yield of corn. This is a typical regression problem that agriculture does. Do we do in economics? Of course, right? All right. So this is actually Xiamen Island. This is housing value on Xiamen Island. Now, if we want to use whether there's a school district, whether there's hospitals, if we want to use this information to predict the housing value on Xiamen Island, that's a regression problem, right? That's a regression problem. It's a regression problem because housing price is continuous. Yeah, it's continuous. Okay. So classification and regression are two broad categories of things we do in many different disciplines. In computer science, in agriculture, in economics, in all kinds of disciplines, we do these different things. And the next topic I want to talk about is called supervised learning versus unsupervised learning. So what are they? Well, Supervised learning is I tell you, so if I tell you what the values of y is, and I ask you to find an algorithm to predict it. So for example, imagine there's a vending machine. Okay, imagine there's a vending machine. So the vending machine has many coins, right? So you throw a coin into a vending machine and you get the things out. Now, we need to write a computer program to tell the vending machine whether the coin you throw into it, is it 10 cents? Is it 50 cents? Is it 25 cents? Is it, so which one is it? Is it $1? Is it 10 cents? Which one is it? It's not that easy. Why? Because they overlap, right? So because each coin is not that precise. So they overlap. So the way that we do this is we let the vending machine measure the mass and the size of the coin. And then based on the mass and the size, I want to predict whether it's a $1, I want to find out whether it's a $1 or 50 cents or 25 cents. Okay? So what is supervised learning? Supervised learning is I give you the data. I tell you, look, these are 10 cents. Sorry, this is $1, this is 10 cents, 50 cents, 25 cents. I tell you this data. And then you basically tell me, find out a method, okay? Find out an algorithm to basically classify them, because this is a classification problem, okay? Tell me which one is. What is unsupervised learning? Unsupervised learning is I don't tell you anything. I just give you a bunch of coins like this, okay? Just a bunch of coins. You do not know which is $1, which is 25 cents. You have no idea. However, I want you to tell me how many different coins there are here, okay? Can you do this? If you only look at these data, can you tell me whether there are different coins? Well, I think you can, right? For example, you can say that, look, this looks like a different coin, right? This looks like a different coin. This looks like a different coin. You just don't know which one, right? Okay. Now, this is harder, right? This is harder. It's very hard to say there are two different kinds of coins. Looks like there's a single different coin here. But at least you can say maybe there are 3 different kinds of coins. Or maybe there are 4, right? This is called what? This is called unsupervised learning. So unsupervised learning is I do not even know what y is, but I want you to find out what? Find out the pattern in the data, even if you do not know what the value of y is. That's called unsupervised learning. So this is a computer science problem, but do we have the similar problems in economics? Of course, right? Of course. Imagine you are imagine you're working for a company, let's say a flight, let's say airline. So you're working for the airline, and the company gives you a bunch of consumer data, and wants to basically predict the consumer behavior. If I raise my price, okay, how will this consumer respond, and how will that consumer respond? Now we know from economics theory that consumers have different elasticity, right? So when you raise the price, people with high elasticity, they stop buying. People with low elasticity continue to buy. And this largely depends on their income, their business travel schedule, etc., etc. But suppose you do not have those data, right? You do not have data on income. All you see is a bunch of consumers here, right? This is how many they purchase, and this is your price. Okay, their price. So what is supervised learning? What is unsupervised learning? Supervised learning is I tell you, look, these guys have high income. These guys have low income. So, they respond more. And then you design a method to basically classify them. What is unsupervised learning? Unsupervised learning is if there are no colors here, okay? If there are no colors, just a bunch of blue dots. And you tell me who are, how to tell them apart, okay? Who are the people with low elasticity? Who are the people with high elasticity, based only on the data but without knowledge of their income. So this unsupervised learning, okay, which we do also in economics. Okay, all right. So that's basically the broad categories of stuff that we will talk about in the first part of this course. In the second part, we will advance. Okay, we will continue advance to causal inference, because in economics it's not enough that we only know how to predict things and finding patterns. We also want to know causal effects, okay? How X causes Y. Not only how X can be used to predict Y, but how X causes Y. That's called causal inference. So the first question is, why do we even need to know? So if I can predict Y, okay? The first question is, if I can use X to predict Y, then why do I even need to know the causal? Why do I need to know how X causes Y? If I can use X to predict Y very well, why do I even need to know the underlying causality? Well, the answer is you can never predict something very accurately for a long time period if you do not understand the underlying causality. Okay? You cannot do that. It's impossible to do that. You can only predict successfully in the short run, but in a very short period. But you can never do this in a long-term period without understanding. Okay? So having learning patterns in the data is not enough. We need understanding. Okay. Now here's a different. This is a little story told by Bertrand Russell, right? So Bertrand Russell says, imagine there's a chicken, and this chicken is actually pretty smart. So this chicken learns the pattern, right? He can learn patterns. So the chicken learns that every morning, when the chicken goes to a certain place, there's somebody waiting there to feed the chicken. Okay, so that's the pattern the chicken learns from experience. So the chicken basically predicts, look, today, if it's not raining, I go there, somebody feeds me. If it's raining, maybe it's late. Okay, so that's my prediction. Okay, however, one day the prediction fails. Why? Because when it's Christmas time, the chicken goes to the place waiting to be fed, and somebody comes and kills it. Okay, because it's feeding time, right? The chicken gets killed. The reason that chicken's prediction succeeds for many days but fails on the final day is because the chicken doesn't understand causality. Okay? The chicken doesn't understand why the person's feeding him. Okay? That's very simple. The chicken doesn't understand why the person's feeding. So without understanding causality, you can only make predictions successfully for a short period of time. You can never make predictions for a long-term period of time when underlying things change. Okay? That's why we need to understand causality. And in fact, that's an argument for science, right? That's actually an argument for science. Why we need science? Because we need to have a model that allow us to predict when things in the long run and when everything changes. Now, the whole discipline is called a causal inference, and the causal inference really have two parts. Okay, if we split it, there are really two sides of causal inference. The first part is called causal effect learning. Okay, causal effect learning. Basically, causal effect learning is easy. We want to learn the effect of X on Y. Okay? Does X have a causal effect on Y? If so, how large? That's the question of causal effect learning. Okay, we're just learning whether X has a causal effect on Y, how much? Okay, how much? For example, if we build this highway in China, or if we build this high-speed rail, high-speed train, what is the effect on economic development? Right? That's a typical economic question. Okay, what's the causal effect of high-speed train on economic development? That's about causal effect learning. The second part is more difficult, which is about learning causal mechanism. And not only about learning the causal effect, but why, how this happens. Okay? So suppose we do our estimation, and we find out that building a high-speed train between city A and B makes both city A and B develop faster. That's causal effect learning. We learn that. But the question is how? Why? Right? Why does this happen? Because it allows people to travel more, or allow the labor market to integrate, or it makes capital flow faster. What is the mechanism that allow high-speed train to make cities develop faster? That's about the second thing, okay? The causal mechanism learning, which is much harder than causal effect learning, right? Which is much harder. Okay. Since you guys have taken econometrics, you don't need me to go through this, but all of you should know that correlation doesn't equal causation, right? You all know this. So this is the gold price, this is oil price, right? The oil price and the gold price. You can see the two are pretty highly correlated, which means that you can use gold price to predict oil price and vice versa. But the ability to do this doesn't mean that they have any causal relation between them. Okay? And so economics is not only about finding correlation like this, but trying to understand why they move together. That's the goal of economics, right? Because we're social science, okay? We're trying to understand. This is a more typical classic textbook microeconometrics example, which is the effect of education on wage, right? So for those of you who are taking econometrics, you probably have done this example numerous times, right? This is kind of boring, but this is a very good example, which is you see that people having more education have higher wage. But that's only a pattern. That's only a pattern. Now the question is there any causality? Is education causing you to earn more, or is it because you have higher ability, and the higher ability people complete more education? Okay, so is it because of education, or is it because of ability? What is the causal mechanism, and what is the true causal effect of education on your wage? Is a typical econometric example of causal inference. Okay. All right. Now, in microeconometrics, there's a whole literature that we have a name called programming evaluation, because economics is a social science, and we try to serve the government. So a lot of economists are concerned about the effect of government policies and how to estimate them. Right. So everything is called programming evaluation. Okay? So, for example, the effect of worker training program on employment, the effect of early child education on later day outcomes, the effect of negative income tax on labor supply. These are all called programming evaluation questions. Okay? So, of course, in this course, we're going to study how to answer these questions. So, and these are typical traditional econometric questions that people answer, right? Economics, in applied economics. Okay, now, if you look at these traditional questions, if you look at these questions that economists today are working on, applied economics, you see that all these questions are actually causal effect learning. They're all learning the effect of X on Y. Okay? If I have a high-speed train, effect on economic development. If I have a training program, effect on outcome on unemployment. These are all causal effect learning. They are not causal mechanism. So how do we do causal mechanism? How do we find out the underlying mechanism of how things work? Well, traditionally, we actually don't, right? We actually do not learn mechanism from data directly. Traditionally, what we do in almost every discipline is that there are specialized scientists who is basically they are called theoretical scientists, whose job is to develop models of mechanisms. Okay, so think about theoretical economists, theoretical physicists. Their job is to come up with models of mechanisms. And then empirical scientists, like empirical economists, empirical physicists, they will go to the data, and then they will use the data to test the model, to learn the model, and use the model for prediction to see whether the model is good. If the model is not good, then the theorist will come up with new models. So that's how traditionally causal mechanism learning works. Okay, so causal mechanism learning traditionally is done by what? It's done by expert. So an expert develop a model, and then we test that model using data, and then and the expert update the model. Is there any way to learn causal mechanism directly from data without an expert developing model, without a human expert developing model? Is there any way to automatically learn causal mechanisms from data? Well, right now, no. Okay, right now, no. But this is a very exciting future direction of research, and in fact, this is the type of research that belongs to the so-called artificial intelligence, AI, right? So this is the ultimate goal of AI. If you ask me, what is the ultimate goal of AI? The ultimate goal of AI is to design robots that can learn causality from data directly. Okay, now so that we do not need human beings, human experts to develop models and then test them using data. We can let the robots directly try to learn models from data directly. So automatic causal mechanism learning is really the next big step, okay, in artificial intelligence. Now, of course, if we can do this, then there's no need for any scientists anymore, right? There's no need for physicists. There's no need for economists, because the robots can the goal is for robots to learn quantum mechanics, to learn relativity by itself, right? Come up with new models, test it. Come up with new models, test it. Come up with new models, test it. Automatically done by robots, right? So this is really the next big thing, but we're not there yet. So today we're still relying on human experts to come up with new models, and we're going to use these models to test them and also to learn causal effects. So that's going to be our focus in this course. Okay, our focus in this course. All right. So so like I said, our course is going to be developed, going to be divided into two parts: statistical learning and causal inference. Okay, so we start with statistical learning, we progress to causal inference. Okay, some pictures. All right, we start this is from So this is from Dante's Inferno, and these pictures by drawings by Gustave Doré. So we start somewhere. We're first going to statistical learning, and then we're going to. But in statistical learning, there's some. So if you know Inferno, how Inferno goes. Inferno is Dante start with at the depth of forest, and then he goes to Inferno, and then he climbs slowly progress to purgatory and finally to heaven. And that's how this course is going to be structured. Okay, so we start with learning, and then we have some demons. What are these demons? These demons are called correlation equal causation, which is a big no, right? So we need to overcome these demons and learn causality, and finally, but causality is not enough, because our ultimate goal is to learn causal mechanism, which is really the goal of economics and science. Okay, and then we can whatever. That's just some stupid stuff. All right. So we begin today with some basic introduction about statistical learning and some basic principles about of what we're going to learn. Okay. So let's suppose. Okay, suppose I give you a variable x and y. Okay, just give you two variables x and y. The first question is, how do we characterize? How do we describe the relation between x and y? The answer is very simple. You just give you the joint, the distribution of x, y, and you are done. Okay, give you the joint distribution x, y, and we're done. We basically describe it. It's easy. But oftentimes our goal is not to describe x and y's, joint distribution. But oftentimes our goal is what? Is to give you x, and I want you to predict y. If I give you x, how do you predict y? Right? That's our goal. Now, if I want to do that, how do I do this? Okay, how do I do this? So I give you a variable x, and I want you to predict y. Okay, how do I do this? Well, let's write it this way. Okay, let's write y equal to fx plus e. Okay? So y is equal to a function of x plus some error. Okay, some error. That's how we write it, right? So our goal is really to find out the best function f that can be used to predict y. Okay, so that's our goal. The question is, what is this f? What is the f? What is the f that can help us best predict y? Okay, do people know the answer? What is the function f that help you best predict this y? Do you know? Any answers? Well, the answer is it all depends on what do you mean by best. Okay? So I say, what is the function f that best predicts y? Well, the answer is it all depends on what you mean by best. Okay? Now, typically when we say it's best predict y, we mean we want to minimize the error. Okay? We want to minimize the error in our prediction. So what is the error in our prediction? It's e, right? It's e. Okay, so I said, okay, I want to minimize y minus fx. Okay, now I have many data points, right? I have many data points. So I have xi and yi. So I want to minimize this. But wait a minute, that's not correct. If I simply add all the error together and I want to minimize it, does it accomplish the goal? No. Why? Because some error is positive, some error is negative. If we add them together, they may be 0. No error, but in fact there are many errors, right? So how do we do? What shall we do? Square, okay? Well, square is very nice, but let me propose something else. Can I just do absolute value? Yeah. Yes, right? Yeah. Okay. I just, negative, still positive, I just turn negative into positive, add them together, that's error, right? That's error. Now if I use absolute value, there is a name for it. It's called what? It's called L1 loss, okay? It's called L1 loss. So L1 loss means we use absolute value to calculate our error, okay? To calculate how much error we're making in our prediction. Now, like you said, I do not have to do absolute value. I can also do yi minus fxi squared, right? Squared. Okay, I can also do this. Is there a name for this? What is it? Sorry? Mean squared error, right? Very good. It's called, right? Is this a mean squared error? Mean squared error, is that the one term you have? MSE, right? MSE. There's actually another name for it, which is called L2 loss. Okay, L2 loss. L2 loss. This is L1, absolute value, squared, it's L2, okay, it's L2. Just different name, okay, just different name. So let me ask you, when you study linear regression in econometrics, do you use this one or do you use this one? The second one. Why do we use the second one? Why do we not just use absolute?
Because it has a smooth function.
Oh, very good. Okay, very good. All right. So let me give you two answers for why we want to use square, not the absolute value. Okay, there are two reasons. By the way, there are many people who use absolute value as well, right? There are two reasons why at the beginning this one is better. Okay, why? There are two reasons. Okay, so one reason is this. This is the true value of y. This is one prediction. Okay, this is the first prediction f1x. This is the second prediction f2x. Okay, f2x. Right. So this is the this is the error the first one makes. This is the error the second one makes. Now, if I use L1 loss, then this second prediction, the error is twice this one. Right, it's twice this one. But if I use squared error, then the second error is what? 4 times this. Right, 4 times this. So when we use squared error, we are what? We are penalizing. We're making a penalty of really bad predictions, right? Okay. So when we minimize these things, when we minimize this or when we minimize this, we're all trying to minimize the total error. But when we minimize the squared error, we're also trying to make sure that none of the predictions is too bad. Because if the prediction is really bad, it immediately doubles the squares, squares and 3 times, right? So it really, really penalizes really, really large prediction errors. So this, when we minimize this, it's about minimizing the error, but also making sure that we do not have really, really bad errors making. Okay? So that's the first reason. The second reason is what? The second reason is that this function is much easier to calculate, right? So because why? Because this has a smooth derivative, right? This is a smooth derivative. This one doesn't have. Okay, so this one is harder to do. This one easier to do, and that's your answer for smooth. Okay, very good. Okay, so this is the reason why we will start using this one. Okay, why we start using the squared error in our course. Okay, all right. Now let me tell you that suppose the goal is this. I want to minimize y minus fx. Squared, okay, squared. So my goal is to try to find a function that basically minimizes the squared L2 loss, or MSE, okay, MSE. My goal is to try to minimize this. What is this function? What is the function that minimizes L2 loss? What is the function? Well, the function is very simple. E y given x. Expectation y given x. Expectation. So if fx is equal to E y given x, then we minimize the squared error. Then we minimize the L2 loss. Okay? All right? Now, if we do not minimize the squared error, if we minimize the absolute value, okay, if we minimize the absolute value, then the best function is not this. Okay, this is not the best function anymore. The best function is, does anybody know the answer? No. The best function is median. Okay, this is called median y given x. It's not median. It's no longer expectation. It's no longer expectation. All right? So let me give you an example. Suppose I tell you a population, right? So suppose I tell you that this is the wealth distribution. This is the wealth distribution of China. Okay, China. Suppose this is the distribution of wealth or income. Everybody in China. Okay, all right. So let's say suppose the highest person, the highest income is 1 million, suppose, and the lowest income is 0. Okay, I'm going to say, this is what? This is 500K, right? 500K. Okay, right. So this is what? This is the median, right? 500K will be the median, right? Will be the median. But the expectation is not 500, right? What is the expectation is probably here, right? Expectation is probably here. Okay, so expectation is what? Let's suppose expectation is 400K, okay? Suppose expectation is $400,000 or RMB, right? This is expectation. Do people understand why expectation is here? Not here? because this is the median, right? This is the middle income. The expectation is because we're taking, expectation, so it's got to be lower than that because we're putting here, right? We're putting here. What is this? This is the most probable income, right? This is the most probable income. So this is probably what? This is probably 200, right? I'm just going to write 200, 400, 500, okay, 500. Now, let me ask you, suppose I just pick a random Chinese. Okay? Just pick any Chinese person out of this population. And you do not know anything about this person. But I want you to predict what this person's income is. Which prediction do you do? 200. Do you do 200, 400, 500? 200. Some say 200, right? Nobody says 500? Nobody says 400? Right? This is what we call the median, right? So I already said, right? This is the median. This is the median, okay? Right? This is the actually I'm sorry. Okay, I'm sorry. I should that should be the other way around. Okay, right? This should be the other way around. Did anyone catch me? Catch my mistake? Okay, the expectation should be higher than the median, right? Okay, so my mistake. So let's say 500. Okay, expectation should be higher. Okay, because we're weighing toward the higher income one, right? Do people get it? Okay. Do people get it? The expectation should be higher than the median, right? Here. So let's say the expectation for 600. Okay, 600, suppose. Right. So this is EY. Okay, so this is EY. This is the expectation. This is median, right? This is the median Y. Now, what is this? This one is the one with the highest probability, right? The highest probability. That's called a mode. Okay, that's called a mode. That's called a mode. So, shall I predict Y to be E or median or mode? Now, many of you says we should predict to be the mode, right? That's what many of us say. Nobody tells me we should predict E or median. The answer is what? What is the answer? The answer is all of your, you can answer E, you can answer median, you can answer mode. It doesn't matter because all of your answer could be the correct answer. Why? Because it all depends on what do you try to minimize. What is the error you try to minimize? Remember, when you make a prediction, right? When you make a prediction, in the end, the result, right? The true income of this person is going to be likely different from your prediction. And the difference is your error, right? Difference is error. So you are trying to minimize this error. But what exactly is the error you're trying to minimize? Are you trying to minimize? So let this, okay, let Y hat, let this be your prediction. Suppose this is your prediction. Suppose this is the true value of Y. The true value of Y has a distribution like this. This is your prediction. The question is, what are you trying to minimize? If you are trying to minimize square, okay, if you're trying to minimize this, if you're trying to minimize the L2 loss, then what prediction should you make? You should predict EY, okay? You should predict expectation. Okay, you should predict the expected income of a Chinese person. Okay, not the mode, okay, not the mode, and not the median. You should predict the expectation. Okay, so if you want to minimize this mistake, if this is the mistake you want to minimize, you should predict the expectation. What if you want to minimize this mistake? If you want to minimize this mistake, what should you do? You should predict the median. Okay, you should predict this person to be 500. Now, when should you do this? When should you predict this mode? Well, if your answer is we should predict this person's income is to be 200, then you are actually minimizing a different loss function. You are not minimizing this. You are not minimizing this. What is the loss you are minimizing? You are minimizing this. You are minimizing Y hat. Sorry, I should write this. Okay. Y hat not equal to Y. Do people know what this I means? Yeah, this I is an indicator function. So this I is what? This I is if true
equal to 1.
Equal to 1. If not true, equal to 0. Okay. So this is also a what? This is also a loss function. It's not L1. It's not L1. It's not L2. It's just it's just a different loss function. And this loss function is what? This loss function is anytime my prediction is not equal to the true value, I get 1. Anytime my prediction is only when my prediction is exactly equal to y get 0. So if I want to minimize this loss, right? This is also a loss function, right? This is also a loss function. This is also something that you want to minimize, right? Because you want to make your prediction equal to the true value. So you want to minimize this. If you minimize this, then you should predict the mode, okay? You should predict mode. Because this minimizing this give you the mode, okay? Give you the mode. So it all depends on what is the loss you try to minimize, okay? What is the error function you try to minimize? You minimize different error function, you get different answers. It's all correct. It's all correct. Just depends on what you want to do, okay? You want to do, right? So as we will learn later in this course, okay? Later in the course, it should. I hope to talk this point again. We're seeing this course. Estimation, okay? Anytime you learn estimation in econometrics, it's actually what they're doing is optimization, okay? Estimation equal to optimization. Now, what do I mean by optimization? Well, you define what you want to minimize, and you find out the answer. That is minimization. But when you do this, you are actually also doing estimation. Okay, so it's the same thing. So we'll do this again in our course. Okay. All right. So now let's come back to this. I give you x, and I want you to predict y. Okay. So I give you x, and I want you to predict y. Now, what is the f? Okay? What is the best f I should try to learn? Okay. What is the best f? The best f is ey given x. If we are minimizing the L2 loss, if we're minimizing the MSE. Okay? In economics, it's called also mean squared error, MSE, right? So if we're minimizing the L2 loss, then f should be equal to expectation of y given x. Right? Okay. But this only answers our first question. The first question is what should this f be? What should this f be? This f should be ey given x if we're minimizing L2 loss. Okay. So that's the first part of the question. The second part of the question is, how do we actually learn ey given x? Okay, how do we actually learn this? What is ey given x? You tell me ey given x, but what is ey given x, right? We try to find out what ey given x is. That's the second part. I think that's the second part. So given the first part, we say fx equal to ey given x is our target function. It's our target. It's the target that we want to learn. Okay, we want to learn. So the first step is I want to find out. I define what is the loss. What is the error I want to minimize? I know this is the error I want to minimize. Then I know ey given x is my target function. It's the function that I actually want to learn from data. Okay, from data, because that helps me to best predict y according to my criteria. Okay, according to my criteria. Just a note on just a word on notation. Okay, on notation on words. In economics. You hear estimation a lot, right? In statistical economics, we say estimation. We estimate. In machine learning, we say learning. So learning and estimation is the same thing. Okay, it's the same thing. When machine learning say learning, it's really estimation. It's exactly the same thing. In this course, we will talk about we'll say estimation, we'll say learning. We just use them all the time. Okay, basically they mean the same thing here. So we want to learn. Our goal is to learn ey given x, because that's the function that helps me predict y. Okay, predict y. So how? Now the second question is, how do I learn ey given x? Well, learning ey given x is very easy if we have all the data. So suppose this is all the data, right? Suppose this is data. This is x. This is y. So our goal is what? Our goal is learning ey given x. So let's start. Okay. Suppose we say we have ey given, what is ey given x equal to 4? What is that? Okay, how do we find out the value for this? It's very easy. Go to x equal to 4. These are all values of y when x equal to 4, right? We just take an average, right? That's the definition of expectation, right? Okay, so expectation is basically taking the average and give it the value, and this is ey given x. Okay, problem solved. So if I want to find out ey given x, I just go to every value of x and then the average y value, just average y, average y, average y at each x, I have EY given x. Okay, all right? And that solves all the problem. We don't need any statistics model, we don't need any econometrics, we don't need anything. That basically is the answer for finding out the answer for everything, right? But the reality is not that simple, okay? Reality is we cannot do this all the time. Why we cannot do this all the time? We may not have all the data, right? Very nice. Because in reality, we may not have all these data, okay? Our data is often limited. Our data often looks like this, okay? This is more like our data, right? This is more like our data. So at this, look at this. At x equal to 4, now this red line, there is no y. There's no y value at x equal to 4. Then if there's no y value, how can we average, right? We cannot average. So how can we find EY given x? How can we find out expectation here? Well, we may, let's do this, okay? One way to fix this problem is to say, okay, at x equal to 4, there's no y, but if we are willing to increase our range, okay? If we're willing to increase our range, we can average every y value next to x equal to 4, right? Okay, look, these values are very close to x equal to 4. And if I believe the y value is kind of continuous here and smooth here, then I can just average all the y values in this small neighborhood, okay, in this small neighborhood. This is what, so instead of averaging y at x equal to 4, we average all the y in a small neighborhood of 4. This is called the neighborhood method, okay? Nearest neighbors. Now, this sort of makes sense, right? So imagine that you're trying to predict the housing value of one apartment, but you do not have it, okay? You do not have it. What do? Well, you look at other apartments very close by, you average that value, and that gives you a pretty good prediction of that apartment's value, right? So you look at its neighbors, average them, and that also gives you a pretty good estimate of EY at x given equal to 4. Okay? So this is called the nearest neighbor method. Okay? Nearest neighbor method. Now it turns out that for nearest neighbor method, we also cannot use it in many actual applications. Okay? We also cannot do this all the time. Why we also cannot do this all the time? Because we may even not have even this amount of data, we may not have. Okay, right? Especially when we go to what? Especially when we go to high dimensions. Okay. Now, this is a one-dimensional problem. Here, x is one dimension. Y is a variable, but x is only one dimension. In one dimension, you go to a neighborhood, you can find all these y values, right? You can find all these y values in one dimension. But imagine we go to 2 dimension, 3 dimension, 10 dimension, 100 dimension. Then imagine we only have 100 data points. In 10 dimensions, in 3, 4 dimensions, this 100 data points is going to be scattered in all around the space, right? So that in really large space, this 100 points will be really scattered around. So that in any small neighborhood, you do not have any data. You do not have any data. So you cannot do this in high dimension, right? So in one dimension, all these data points is in a nice small neighborhood. But once you go to high dimension, 2, 3, 4, 5, they're really everywhere, right? They're really everywhere in the space. So you cannot do the same thing again. Okay? So this is called what? This is called the curse of dimensionality. Meaning when the dimension is high, you cannot do this. Okay? You cannot do the average thing anymore. Okay? Even if you have enough data, even if you have lots of data, if the dimension becomes high enough, you cannot do this. Or if the dimension is low, but you do not have enough data, then you also cannot do this. Okay, you also cannot do this. Then what can we do? If we do not have enough data, or if the dimension is high, what can we do? If we cannot do averaging, what can we do? Right? What can we do? Well, then comes our old friend that you're all familiar with, which is linear regression. Right? So how does linear regression help? How does linear regression help? Well, linear regression helps because linear regression doesn't need a lot of data, right? Okay, so think about this. If this is x, this is y, and we have all these data points. Okay, we have these data points. So these are the data points we have. Okay, these are data points we have. Now, if I want to do averaging, if I want to do nearest neighbor, the neighborhood averaging, suppose x is here. Okay, x is here. Then I take this neighborhood When x is here, I take this neighborhood, which is only 1 point, right? X is here, I take this neighborhood. This is called nearest neighbor average. But it needs a lot of data. But what if I do not have lots of data? Then, okay, suppose I don't have this data. I don't have these data, okay? I just don't have these data. I only have this data and maybe these two. Okay? Then there's no way I can do averaging anymore. But I can still use linear regression. Right? Because how many data points do I need to draw a straight line? 2. Okay? So I only need 2, and I can do a linear regression. So when you do not have enough data, or when your dimension is low, what do? You will need a model. You need a model. Now, when we do averaging, okay, when we go like this, when we take this neighborhood and when we do this averaging, we do not have any statistical model. We do not have any model of the data. We'll just do average here, average here, average here, average here. There's no model. There's no model. But when there's not enough data, then we need a model to describe the data. Okay, so that brings us to a key difference. Okay, the two key terms in statistics and econometrics, which is called parametric methods and the non-parametric methods. Okay, so non-parametric methods are methods that do not assume a model. There's no model. Okay, there's no model. So the neighborhood averaging is a typical non-parametric method because there's no model. We're just doing averaging everywhere. Okay, there's no model of the data. Now, on the other hand, what I can do is I can use parametric methods. Parametric methods are basically assumes a model of the data. For example, what is linear regression model? What is the linear regression model? Very easy. Fx equal to what? Equal to beta 0 plus beta 1x plus beta 2, right? So this is the typical linear regression model. The model assumes that it's a straight line, right? So basically, linear regression says what? Linear regression says fx, which is equal to ey given x, right? Now, for non-parametric methods, I have no model. I'm just going to average. But for linear regression, I'm just going to assume that this is beta 0 plus beta 1 x. This is called a model. Okay? This is called a statistical model. Okay? When you assume this model, then it makes things much easier, right? It makes it much easier because you can just draw a straight line. Even given you 2 points, you can draw a straight line. And then you can predict the y value at any part of x, right? Any part of x. That is a parametric method. Okay, that's a parametric method. All right. Okay. So this is all right. Okay. So this is reason why part of the reason why we need parametric models, not just non-parametric methods. Okay. All right. Now, typically, when you take econometrics, they don't really start this way. They start with linear regression. But really, there's no reason to start with linear regression because because in my view, we should start with non-parametric. Right? Non-parametric. Just tell the original way you should do it. We have enough data. But if you do not have enough data, now let's try something parametric. But even if we try parametric, there's no reason we should try linear. Okay, there's many different models we can do. So, for example, right? Let's say, okay, suppose I give you these data sets, right? Suppose these are the data points. Now, if I want to do parametric, meaning I want to use a model, but I don't have to use a linear model. I can, this is a linear model, but I can also use other models. For example, this is a polynomial model. This is a square, okay? This is a square term. So this is what? This is this is beta 0 plus beta 1x, right? It's the linear one. The second one is beta 0 plus beta 1x plus beta 2x squared, right? X squared, right? Okay? So, which is, square term. And that give you a line like this, right? That give you a line like this. Which one should I use? It looks like this one's better, right? Why? Why? It fits better, right? It fits better. But I can do even better than this. If my goal is to fit better. Okay, so how do I make it fit better? Well, look, I can do this. So suppose I have 1, 2, 3, 4, 5, 6, 7, right? Okay, so that's okay. So these points. Now, I can do a linear regression. I can do a polynomial like this. But I can make it even fit better. What I do? Right, I can do this. I can do this. This is also a model, right? This is also a model. And I can actually write out the equation for this model too if I want to. This is also a model. And this model gives you what? No mistake, right?
Yeah.
It completely fits. So, is this model the best model?
No.
Is this the best model? Right? Okay. The answer is no. So basically, when I ask you why this one is better, right? I say, okay, why is this one better? You say this one is better because it fits better. And I say that's actually not quite correct, because it's not always better to fit better. Okay? Because why? Look, this is the one that fits best, but it's not the best. So how do we determine which model is the best model? Well, that's the topic of next lecture. It's also one of the key messages of modern machine learning that's going to be really helpful to our understanding of data analysis. Okay, so that's going to be next time on Thursday. Okay, on Thursday. So we end today here because I promised to end the lecture 10 minutes early. Just quickly, two things. The first thing is, if you want to take this course, if you plan to take this course, make sure that you do, hold on. Where is it? Sorry. Task 1. Okay, so make sure you do this, right? Make sure you register on Moodle, which is the, which is our for homework, right? Raven is the password, and then make sure you register on Piazza. And you may need to use your XMU address. Okay, you may need to use your XMU address to register for both. Find this course on Moodle under WISE at 2018-19. And then please go to Piazza and answer the 3 polls. Okay, the poll is about review session, your programming, your background. Okay, your background. So please do this after class. And also, I would also like to ask all of you to join the WeChat group. So this is what I'm going to do. I'm going to use the WeChat group for announcements, okay, for course-related announcements only. And I'm going to use Piazza for, for academic discussions related to this course. And I'm going to use Moodle for homework. Okay, so that's, the classification. So Xiaoqing will actually show you the QR code for WeChat group. So please join that if you are interested in taking